right? Just previous model we talk about in general 3D model, 3D structure. We have a 4-column, 1 slab element with a uniform load. We just understand how ETABS handle and distribute the load, uniform load to each adjacent support. So simple. It's supposed to be simple. Even though geometry is complex, you may think something's bring the same knowledge, try to figure out what is more general approximation approach. So you may have to just continuously think about it, and then using FM model and verify whether this is kind of good enough or not, right? We've been practicing homework 1 and 2, you're not going to get the same answer. There's always slightly off, right? In theory versus finite element structure is slightly different. But is it okay? It's not okay. You are the one you need to develop, right? Right? Maybe less than 5-10% might be still reasonable, but not more than 10, 20, 30%. If you end up with something 20% different, 15% different, you need to think about it. Obviously, SQL cell potential mistake in your input and any boundary condition or any input mistake, right? Don't just ignore it, because still theoretical model and FM model should be very close enough. It's acceptable, should be acceptable range. But if you found something wrong answer, different significant answer output, SQL cell recheck it. Most of cases you made a mistake somewhere. Usually we make a mistake in unit. Sometimes you type it 1 inches, but you may end up to type it 1 meter, right? So a lot of mistakes. So I want you to keep, right? Practice somehow internally. You need to come up with QAQC procedure. It's very important, right? So now let's talk about this. Okay. You know, before you do that, I'll make one, shrink it down, and then move on to it. So this one's one story. So okay. So what I try to do here is now show our still framing. So I'm gonna delete. So this is Control D. Okay, so this is one single story. Now the previous model is only has a column and slab, but now this model is similar, but we're using steel beam and metal deck slab, right? So now let's take a look at it, how this model works. But what we need to understand, hold on a second. Oh, this is another, okay. Okay. So I'm gonna show you extrusion. Okay, you see that extrusion? You see that we have a H shape, W shape, column, border, and beam, right? The difference between these two is only orientation of beam. Let me see, is that? So I'm gonna turn off the extrusion. Yeah, this is also interesting. So this model, let's check it. I'm gonna put it on plans. And then you see that this slab is 3-inch metal deck. What should your name? 3.25-inch lightweight concrete. 3-inch metal deck, 3.25-inch lightweight concrete slab. So you saw go to define section metal deck slab. So this is 3-inch metal deck plus 3-inch metal deck plus 3.25-inch lightweight concrete. So here metal deck steps 3 inches, concrete is 3.25, so for the 6.25 slab we are using. So just interestingly, this is you should actually observe why what this arrow means. What this arrow, what does this arrow mean?
Are they one-way slabs?
Yeah.
So that's
So metal is collocated, so they should be sitting on every beams, right? Right? Because they are collocated. So they have to span this. Basically, metal deck slab, when we use it, right? Look at this. We need certain beam spacing, right? So currently, I'm just give you the 3-inch plus 3.25-inch metal deck is typically for office floor. We use it in many cases with 10 feet space, 10 feet, 10 feet. This one's inside will take it maybe a little bit more, less. This is, let me check the dimension. I forget. So let me turn off this extrusion and Control D. All right, 360. Let me change to unit to feet. Okay, 30 feet. Right? 30 feet divided by 3, so 10 feet, 10 feet. Let me check here. It's maybe 24. But this is an example I use. Yeah, 24 feet, right? So this is one example. Maybe this is the steel column, steel beam is older, and metal deck slab is the system we're gonna use it for your office building design. The reason why in general, why do we have to use a steel beam, not concrete, right? Because kind of one basic primary reason is the span, space requirement. Office space, typically office environment, you want relatively long, big space. Just co-working space, office space, right? So I gave you 30 feet, this example, right? Span could be typically a little more, 40, 45 feet. Sometimes more than that. Residential building, when you visit your house, measure your room size. Okay, living room size. Look at it. What is dimension? Residential usually smaller than office, space-wise, right? Your room might be maybe 15 by 15 or something plus minus range, right? But they don't need 40 feet, right? 45 feet span. So office space, commercial office is typically 30 by span. Column spacing is 30, and this is about 40, 45 feet. We'll find out some example I will show you. But anyway, so engineer now says, okay, using one is left, this one is left, right? The same as the concrete. If we use same one is left, it's going to be identical. But this is not steel column, steel column. It's going to be all concrete column, concrete beam. But slab is one is slab, same as this, right? The only material is different. But put it away the concrete. We're going to talk about the composite beam, this steel. Then what we're going to do, since you already know it, your homework, your steel class, bring it. You design the beam a lot. If you take the steel class, bring it. I'm sure you learn it. You design the steel beam. But I'm not sure. You probably textbook show like one beam. So you probably design one beam. Do you remember that? Right? Or sometimes they only give this steel beam, right? And it's like this. Let's say 24 feet length. Now dead load, maybe it's still a step give, yeah. Dead load is self-weight. Live load either 100 psi, let's say, The self-weight we need to calculate for 3 metal depth plus the 3 current live rod, concrete topping. So we calculated if this is live concrete, this is we take 3, it's divided by 2, another 2, 3.25. So this is 1.5 plus 3.25. Look, this is about 4.75 inches. So divide by 12 to make an fit times live concrete 115 PCF. So this is roughly 40 something 5 to 8 PSF, including metal deck weight. So we roughly can calculate weight of metal deck slab equivalent weight by using just converting to a flat relative flat concrete thickness, equivalent thickness, and we should be able to calculate uniform weight in uniform load, right? So with that, obviously okay. So this beam supposed to take this slab loading, which is we have let's say 50, 45 and 100. So now this is area load. We need to convert to line load, right? W that W line load. So 45 PSF times what? Tributary width, which is tributary width is what? 10 feet, right? 30 divided by 3, 10 feet. And just repeat your, I think, step flat. So this 10 feet, so that 450 pounds per foot. This is equivalent line load, which this beam is supporting for that load case. For line load, 100 PSF times 10 feet curvature width, right? It's 1,000 pounds per foot. So this is line. You should be calculate generally looking loading area loading time curvature width. You can calculate convert it to line equivalent line load, right? Since we know this line load, let's say 1.2 dead load plus 1.6 live load, which calculate 1.2 times 450 plus 1.6 times 1,000. So we should be calculate the total ultimate line load, that plus live load, right? This is ultimate load. So now what do you need? Moment is right. W ultimate times length square divided by 8. You can calculate the moment at the middle span, right? The shear is simple. Whatever is total load is W times length divided by 2. This is each reaction. Because it's uniform load, all the total load divided by 2 goes to each end. So this is something you could simply calculate. You should be calculating the moment diagram, moment at the middle span and shear, right? Let me see what I have here. So data load, okay, so there. Instead of 100 live load, I have 70. Let me just change the live load to 100, and then I'm gonna run it. So assign area loads to uniform load. Data load is automatically calculated. Live load I convert it to reassign, replace to 100 PSF. So again, basically I have live load 100 here, right? Dead load is self-weight. So I'm gonna run the model. Anybody can calculate this? Calculator? 1.2 times 450. I think just I assume 45%. 1.2 times 450 plus 1.6 times 1,000. So what is the total? 2140. 2140 pounds per foot, right? So let's say roughly 2.14 kips per foot, right? Right, 2.14, right? So, okay, can you calculate the shear? 2.14 times 12, let's use 20, so So 24 divided by 2. 24 feet divided by 2 is a shear. So what is this? 2.14 times basically 12.
25.68.
25.68. Okay. Something like that. What about movement? 2.14 times 24 square divided by 8. So maximum moment.
154.08.
Oh,
4.08.
1.008. Keep it. 154.08. Right? This is hand calculation. We'll confirm this. Let's see. So basically again, ETABS has a section property 3-inch plus 3.25-inch live So automatically they calculate the self-weight. And the live load I assign area load 100 psf, right? See that 100 psf, right? So do I have a load combination 1.2 that? Let me create the 1.2 that. So 1.2 that and 1.6. 1.6. So 1.2, 1.6 library. Okay, let me check the moment. From the combination 1.2 that, let's check the moment. So what do we have? Oh, a little bit difference. Let me see, because I think self-weight might be slightly off. 171. So keep. I'm gonna change to keep.
You don't want to change the feet.
171 versus 154. Now there's some power discrepancy might be happen. Oh, beam weight. We didn't include a beam weight, right? Then let's check only live load because we didn't consider. So live load moment. Let's check live load only pure 1000, right? So the moment 1.0 kip per foot times 24 square divided by 8. What is it? 24 square divided by 8.
72.
72? Okay, let's see. And it 72. Right? Because I think something, because the self-weight of beam wasn't included here, so we end up with a little less. Or maybe this one we using 45, but they may using overall 48. That's a slightly this, but usually should be matching. So we confirm that live roads, obviously we calculated, right? Length times the length square divided by WL square divided by. Remember this. PL divided by 4. WL square divided by 8. Moment. Remember this. This is only two formula. Especially WL square over 8. You're going to cover most of your engineering work. Because most of engineering work has a problem, is typically slab and beam. Right? Slab and beam problem. Even yesterday, I went to Union City. Yeah, I took a photo. I'll show you. There's a roof, 6-story building roof has an issue. Right? Why? Somehow it pitched roof, but in the middle lowest floor, they put some old air handling unit. And the floor below your unit has some girder is sagging. Right? So contractor asked me to come out and see what's going on, and they already start working, but they're not somehow confident. But obviously, I see that huge beam kind of sagging. I'll show you. Oh, not here. Wait a minute. later. I already downloaded. But anyway, the beam, in order to checking beam your stress level, right? Demanding versus capacity level, you need to estimate what is current loading conditions, right? Maybe, you know what? When I visit the doctor's office, what they do first, always asking me, sign up, shit, right? And then nurse always asks me to go up to scale. They measure the weight. Same thing. Beam, right, was initially designed for southern design load, but this building was built 100 years ago, right? How do I know what was the original their design and capacity, demand capacity ratio? I don't know. No record. But I had to somehow, using my engineering judgment, to understand what is up there, material on the roof, and what is a beam size, wood, what is the weight of the wood. Depends on the wood species, the weight is substantially different, right? Old kind of, especially even the pine, southern pine versus white pine, their weight is almost 50% different. So you need, for in terms of wood, you need to really more specific because material, steel and concrete is engineered. So we kind of come up with something more kind of consistent weights, right? When we build the structure, our concrete and steel weight is pretty much consistent. But old wood, some people using different wood here, there. Wow, their weight is different. Capacity is different as well. But anyway, so what I try to introduce you, this is simple task. So far, I didn't do any crazy engineering stuff, right? To me, this is not even engineering, this is college level math. I can teach proper elementary school. It's not really serious math. Is it serious math? They learn more than this, right? But difference is we try to connect math with the physics, right? Somehow we need to understand geometry, right? And the loading, right? How does the load is kind of apply and what kind of external force, how that creating some apply and generate the internal forces. We're talking about internal forces, shear and moment, and deflection, right? Eventually, this is the beginning. Most of building, we need to start from the slab and beam, and then gutter, and then column and foundation, because this is how the load actually going down. So this is simple math, but very important, right? Remember the WL square of A. This is a uniform load basis, but in order to get this level, you need to understand the geometry, right? The space, how this structure element is spanning, right? X orientation matter that. If you rotate 90 degrees, what happens is totally, you're gonna end up with totally wrong answer because the metal deck should be perpendicularly span and sitting on the beam. And now ETABS, this metal deck slab can load it, transfer the load properly. If you rotate 90 degrees, you probably get the wrong answer because the loading is somehow they dump it from here to here, right? Which is not reality. But you may get some number, but totally those useless. But thing is, I want you to kind of bring this all together. Now, physical, how the building is constructed, and associate load paths. You need to understand, properly define the load path. That is most important things. Next step is mostly straightforward. But up to here, right? You need to understand basic of material, weight, load paths based upon your structural geometry, right? So, so this is actually the one of example we did. So let me just show both. Exaggerate. So, so moment diagram. So let me see. Okay, I'm gonna turn off this. So now a little bit background. So this example, I made it. Maybe I'll share shows one thing, and this is very because a 3D structure. Somehow, when you run it, you need to understand also electrical stability. Otherwise, ETABS gonna give you the instability error message, warning message, because we building the model in 3D, right? We follow X, Y, Z coordinate. We build this 3D structure, right? Vertically loading is all the way down, typically no issue, but when we build it, the ETABS is internally, they analyze it and see this building is stable or not, naturally. So with that said, I intentionally, in order to make this example, what I did is I need to column and border. You see that red color, right? Yellow color, right? Why are we getting this red? What is yellow means? Right? This is a positive moment, right? Typically in bending moment diagram, we draw it on the tension side, but they're using yellow color because this is color setting, right? Yellow, they show positive moment, but negative moment, they show on, they're using red color, right? So our case is in pillar beam is pin-pin connection, right? You study, you know that what is a pin-pin, simple pin-pin connection. No moment resistance. That's why zero moment, zero moment. You have a maximum moment at here, right?
What do you mean negative color?
Then the negative moment. So, eventually.
Failure?
Okay. So, okay, if this is for steel and concrete, there is something probably agreement. So one thing is everybody know this, right? Simply supported beam. So moment diagram like this, right? If we have a gravity load. But now this, right? We usually draw the moment diagram like this. So P times L, right? So moment here is a P times L, right? We draw a moment on the most like the tension side because this is deflect like this. Tension force is developed at the top side. So this is maybe one kind of negative. We usually somehow we call this. Also, if you maybe draw a moment frame like this, concrete or steel beam, but it's moment frame. This is connection. If you have a gravity load, our moment diagram is like this on the beam because we have a moment resistance, right? Here, moment frame. See that this frame? Double curvature. You want to do this in gravity load? You're gonna same thing like this. Maybe we can build it. Because this is a connection. Going back. I think we maybe can generate something other stuff column too. But see this curvature on the beam because this is connection. Also, you have some double curvature, right? This is a fixed condition or rigid condition, so you have double curvature, double curve deformation because we have rigid connections. Now, but simply supported connection like this, obviously the member will bend like this, one single curvature. This is engineering or this is what it is. To me, this is just physics. This phenomenon, when we have some rotational resistance, right, you see that behavior like this. So obviously we found it, mathematicians come up with some formula, try to explain this, right? So obviously what you see here, I'll show you, okay? So at least remember that one single curvature means simply it's a pin-pin connection. So when you have some loading events in one way, create the so if you have this pin, it's gonna bend like this, right? Can you hold it here? How can I bend it? You hold, don't get it there. Yeah, right. This one. So this, if you holding providing rotational resistance, it's gonna bend like a function. See something like this here, right? But if you loosen, it's gonna bend like this. I think this is something that we're talking about doing restraint. So it is happening here. So again, how do I know here? So I'll show you here because this is numerical. So let me zoom in. Because this is more, because the 3D model, I need to add some more here. Yeah, I need to increase the font size. This is, do you see the dot? Here, dot?
The dots.
Yeah, that means the moment release. So we basically, I release the moment, which make try to pin connection. So the question is, I will kind of give you just a physical example. So this is flow framing system is common. We using this analysis everywhere, most likely. But typically, eventually our buildings, we have a backbone of concrete shear wall, column and beam. All the column is just straight column. So that means any steel beam and boulder is not part of electrical system. So this is only for gravity flow framing system. But this model, I intentionally, otherwise it's gonna give us the instability. So I make this boulder is part of rigid connection, right? So you see that negative moment. Well, this one doesn't have a negative moment. You see the only single curvature moment diagram, right? Because I release the moment, right? So what is reality moment or release the moment? I try to connect, explain in steel construction what is really simply supported connection. I think you still class. I'm not sure you do you have an AIAC manual? Probably you didn't buy it. Very expensive, right? But this is older, right? Right? I'm just cut the section here. Try to show the section to looking like this. So this is moment frame border, right? I have a beam one side coming like this. It's double shape. Flanges, flanges. So this is border. So I have some vertical stiffener plate and bolted connection. Right? This is vertical stiffener plate, bolted connection. Have you seen it? And if you want to see it, metal deck is spanning like that. And concrete is pour on top. Right? We just assume this is a pin connection. Eventually, this is not 100% pin because we have a multiple group of both. We have some rotational resistance, but we just simplify. This is good enough, right? We could assume this simply supported beam. So this one side connection, right? This is pin connection, right? Because our connection is happening at the middle web. If something pushing it, this has a tendency to rotate here because there is no much rigidities, right? Then what is moment connections here? We need to provide additional top and bottom restraint. So typically we need to provide another plate, bolted and bolted. And this one somehow we need to provide either a couple of different way. So we need to bolt it and provide this top and bottom flange is create the restraint for the rotation. So some additional connection plate and bolt connection is needed for make the moment connections. But we'll get into that. But typically, beam frame, I want you to at least understand today clearly because you've been practice this a lot. Basically, 99% is something like this, right? If you're living in a dormitory or house, your beam, wood joist, simply support beam. They don't have a rotating and rotational resistance. It's simple beam. Then you're using WL square of 8 for your beam moment calculation. This beam, even still, doesn't matter, tall building or any. Most likely, if you see the multi connection like this, only web, this is a web, right? Web to web multi connection is simply support simple connection, right? Doesn't generate any rotation resistance. So we typically our intention this pillar beams work like a simple beam. In order to do that, we need to reduce the moment. This is more numerical the feature in order to make analysis run based upon what we need. We typically designer try to define the moment restraint. So just the last one, click the beam. When you turn on the property, you see that angular moment about we get showing this was released. So at least this is something that I want you to kind of run this model, think about it, just double check the moments, right? Based upon the loading, just hand calculation, confirm, simple math. I'm just keep doing the homework 1 and this is homework 2, right? It's similar to the homework 2, but homework 2 is just simple beam model. But now simple beam model in the 3D model, this is how connected, right? So we're gonna just keep kind of moving up to the more 3D scale, but same concept. I want you to understand clearly basic, right? Homework 1, we're gonna go back to the homework 1 later for the when we talk about electrical system, right? You know, you can visualize now a little bit clearly now. This one, I don't at the time. What the heck? I don't understand how this guy applied to in the reality. This is total the connections. All right. Any question? But I want you to keep working on the homework 1. Is everything's matter. You need to practice and also even practice punching the calculator matter. Try to minimize any mistake punching the calculator. But everything's I want you to follow catch up. So next ones we're gonna spend more time to design the beams based upon the loading, right? So bring your project flow plan, right? Find out, look at any example of building. Bring your building flow plan, right? Your team, you need to choose the team project. Building next week. We're gonna talk about in general planning, right? This is just engineering, just strategy I try to give you. Now, next one is part of design and planning. So we need to kind of learn where to put the column, how, right? Right? And how about the wall location? This is something planning. So we need to talk about in general, and we need to combine all this while we are moving. So this is very important. You know what? One thing that I like to share you